These numbers are all palindromes, meaning they read the same forwards as they do backwards, and they're also all multiples of 11. So are all palindromic numbers multiples of 11? Well, not quite. For example, 111, 131, any single digit number, and many others are palindromes but not multiples of 11. But there is something else that all of these numbers have in common. They all have an even number of digits. And as it turns out, it is true that all palindromes with an even number of digits are multiples of 11. I recently came across this problem whilst listening to a podcast, and it immediately drew me in. I teach lots of classes on maths challenges and Olympiads, and this problem uses exactly the kind of maths that we cover there, so I really had to figure it out right away. I'm going to show you why this is true, but before I do, why not pause and try it out yourself? Or if you're ready, let's state the problem really clearly, and then we will dive straight into the solution. We're going to show that palindromes that have an even number of digits are always multiples of 11, and that's not always true if there are an odd number of digits. And in particular, I want to say something a bit stronger, which is that whatever the number of digits is, if it's an odd number, you can always find a palindrome that is not a multiple of 11 that's that length. So a palindrome is a number, or a word in fact, that reads the same forwards as backwards. So for example, 3162522613 is a palindrome because you can read the digits forwards or backwards, and it is the same number. When you're tackling a problem like this, the best thing to do to start with is to play around with it a little bit, and I would encourage you to pause the video and see if you can work out some of this for yourself before you watch on. But we'll just test it out with a couple of numbers. For example, if I did 134431 and I divide it by 11, I do get 12221 with no remainder. But if I do it with 1563651, I get 142150 with a remainder of 1. So in the odd case there, we've got something that's not a multiple of 11, although sometimes we would get a multiple of 11, but we don't always get it. But for the even case, it's going to turn out that we do always get a multiple of 11. So at this point, we haven't proven anything, we've just got the problem into our heads, and it looks encouraging. So let's start by proving that palindromes that have an even number of digits are always multiples of 11. So if we start with the 2-digit palindromes, well, that's 11, 22, 33, 44, and so on. That's just the 11 times tables. So we can say that any number of the form AA definitely is a multiple of 11. When we go on to 4-digit palindromes, 1001, 1111, 1221, and so on, now it's far too many just to check all of them, but we can say that they are of the form BAAB because they're palindromes. And you could write BAAB as B00B plus AA, and of course B00B is B times 1001, and AA is the number we've already considered as a 2-digit palindrome, that's A times 11. But 1001 you can factorise as 91 times 11, so actually 1001 times B is just 91 times 11 times B, so overall this number that we've got here, BAAB, is 91 lots of B times 11 plus A times 11, or 91B plus A times 11. I'm adding two multiples of 11 together here, B00B and AA, so when I add those together I get another multiple of 11, and so any 4-digit palindrome really is a multiple of 11. At this point it seems like a bit of a fluke that 1001 is a multiple of 11, and it's not obvious that we're going to be able to keep doing this, but in fact we can. So if we look at 6-digit palindromes of the form CBAABC, well, that would be C0000C plus 10 lots of BAAB, but BAAB we've already shown is a multiple of 11, that's our 4-digit palindrome, so 10 times it is also a multiple of 11. So I would just need this number that I'm adding on, C00000C, to be a multiple of 11, and again that's C times 100001. So if that number, 100,001, is a multiple of 11, then the 6-digit palindromes will be a multiple of 11 too. We'll come back to that, but we'll just look at 8-digit palindromes as well, so that's DCBAABCD. Again, now you see I just have to add on this number D with lots of zeros, D, plus the number we've got as a 6-digit palindrome times 10. So by exactly the same argument, if I can show that 1 with all of those zeros, 1 is a multiple of 11, and all of the previous numbers like that are multiples of 11, then it's going to show that all of these numbers are multiples of 11 at once, and I can then clearly add on 10-digit palindromes that would have E with lots of zeros, and then an E, and so on. So all we need to do to show that our result is true is to show that this number 1 with lots of zeros, and in particular notice it's always going to be an even number of zeros because I'm always adding on 2 extra digits each time we go up, because we're just looking at even numbers of digits. If that's always a multiple of 11, then all of our even digit palindromes are multiples of 11 too. So how do we show that? Well, we'll just start at the beginning. Well, 11 would be the simplest one that doesn't have any zeros. That's just 11 times 1, clearly a multiple of 11. 1001 we've already seen is a multiple of 11. But if we write it in this way, it reveals something. So if we write it as 990 plus 11, then that's 90 times 11 plus 1 times 11, which we already know is 91 times 11. If I then add 2 extra zeros in to get 100,001, then that's 99990 plus 11, and actually that then you can see is 9090 times 11 plus 1 times 11, so that's 9091 times 11. As those extra 2 9s at the start are just 9000 times 11, if you like. If I add 2 extra zeros in again, we can keep playing the same game. We get then 909090 times 11 plus 1 times 11, which again is a multiple of 11. So we can see that at each step here, we are adding firstly 90 times 11, then 9000 times 11, then 900,000 times 11, and then finally 90 million times 11 would take us to the next step where I could add in another 2 zeros and show that this is true as well. And so you can see here that it really is true that all of these numbers are multiples of 11. We can just keep going with this process, keep adding 2 more zeros as many times as we like, and all of these numbers will be multiples of 11. And so we've shown then the first part of our proof that all palindromes that have an even number of digits are in fact multiples of 11. So let's look at the second case that says for any odd number n, there's a palindrome with n digits that is not a multiple of 11. So it's not the case that all palindromes with odd numbers of digits are not multiples of 11. In fact, some of them are. For example, 121 is 11 times 11, but if we did 131, that's not a multiple of 11. In the 5-digit palindromes as well, 14641, that's 11 to the power of 4, so that's a multiple of 11. But if I changed it to 14741, that would not be a multiple of 11. And then for a 7-digit palindrome, I could do the same thing. 123431 turns out to be 112211 times 11. You can't always use this structure, by the way, to get multiples of 11. But if I change that middle number to a 5 instead of a 4, then it's not a multiple of 11 anymore. In the first case, I've added 10 to the number. In the second case, I've added 100 to the number. And in the third case here, I've added 1000 to the number. And that's going to be the key to showing that we can always find a number here that doesn't work. So suppose we can find a palindrome with n digits that is a multiple of 11. Actually, rather than saying n digits, I'm going to say 2n plus 1 digits, because 2n plus 1 is our standard form of an odd number. That will make things a little bit easier. Now, if no such palindrome exists, then we've got nothing to prove, because clearly there's at least one that isn't a multiple of 11 then. So let's write it down like this. I don't know how many letters there are here, so I can't just use A, B, C, D, E. Let's call them A1, A2, A3, and so on. If there's 2n plus 1 digits, the central number here is going to be an plus 1, the n plus first digit. There'll be n digits before it and n digits after it. So here's an example of what that palindrome might look like here. Now, if we add a 1 then to the n plus first digit like we did in our examples, or we're going to subtract 1 if it's a 9, that will keep the number a palindrome, right? If I've got an 8 here, I can increase it to a 9, it'll still be a palindrome. If it was already a 9, I can't add 1, but I could subtract 1 and it would still be a palindrome to get back to the 8. And then the resulting number is larger, or smaller if I've subtracted, by 1 with n zeros after it. So that's just the number 10 to the power of n. But 10 to the power of n, a 1 with lots of zeros after it, is just 2 to the n times 5 to the n, because 10 is 2 times 5. So the only prime factors of a power of 10 are 2 and 5. So we know that 10 to the n can never be a multiple of 11. So the number that we're adding on here or subtracting is not a multiple of 11. But the palindrome we started with is a multiple of 11. When you add a multiple of 11 to something that's not a multiple of 11, you get something which is not a multiple of 11. So this new number we've found is always going to be a palindrome, which is not a multiple of 11. So I think that's a really interesting result, and if you enjoyed that, here's another challenge for you. Can you find 5 consecutive integers that multiply to give 360, 360? Have a think about it, and watch this video if you'd like to see my solution.